which is unlocking potential in AI-driven materials research. Now, in this session, ladies and gentlemen, you will have the opportunity to discover actionable strategies for translating advances in AI material research and how you can develop them into real commercial impact. And also as well, our next speaker will be very happy to hear from you. I'm going to flash this QR code on screen for you right now to use Pigeonhole, which is the platform that we're using for all of your questions and queries and comments to come through. If you're on the browser, you can type in pigeonhole.at and enter the password beyond. So please ask as many questions as you can during the session. Now, ladies and gentlemen, powered by EDB and A*STAR, we're very excited, of course, to bring on our next speaker, our Vice Provost for Research and Enterprise, and the Amoris Ambrosius Chair in Material Science from Imperial College London to give a presentation, of course, right now. Ladies and gentlemen, wherever you are in the hall at Beyond Stage, do me a favor, put your hands together to welcome on stage our next speaker. Please welcome Professor Mary Ryan.
It's working? Yeah, it's working. Here we are.
Welcome.
There's Mary Ryan. And I am a material girl, so thank you for that. Right, so thank you. I have to say I am delighted to be here. I'm a slight imposter, so as you will see, I'm an experimentalist, so I'm not an AI computer person. And so I'm standing here a little bit as a skeptic, right? And so one of the things I want to, I guess, present today is some of the challenge areas where I think AI has potential, but we have to be really careful that we think about the physics of the system in order to get some of the right outputs. My job at Imperial, I'm also responsible for our enterprise department, so all of our IP spin-out commercialization sits in my research portfolio, in my portfolio at the university. So in that space, we have a lot of thinking around AI potential. At Imperial, we've got about 300 academic groups working on various aspects of AI, including AI materials. We have about 10 AI startups a year coming through. So we've got a lot of people doing this. And we've been thinking a little bit about what are the mechanisms to support that. So I'm going to do a little bit of two kinds of talk, my materials perspective and then my innovation space that we have at Imperial. OK, so if you don't know Imperial, we're an institution in London and now in Singapore, so we're very delighted to have our global presence here. Founded in 1907, and this is our founding mission to be useful. So if we're not being useful, then somebody should tell us here in Singapore. We're #1 university in Europe. We have a lot of industrial engagement, 500 partnerships a year, and since 2019, about almost 300 startups. So we're a very innovation-focused university. As part of our strategy, these two main pillars sit in my portfolio at the university. OK, so I'm a material scientist. Materials, it's the story of humanity. And you can think about the history of how we've thought about materials by, we started off with serendipity. People accidentally found things that made a difference. So you'll see a picture there. This is a stained glass window from a cathedral in Norwich from the 1400s. It's red because somebody put some gold into molten glass for luck. It turned into gold nanoparticles, which gave you this red color. This was an entirely accidental piece. But we think about humanity as Stone Age, Bronze Age, Iron Age, Silicon Age. Then we moved into materials by necessity. We had an industrial revolution. We knew we needed certain types of properties of materials. We did lots of experiment, and this is really the dawn of experimentation. We knew what we wanted. We had large industry labs. That's how we got materials. Now, this is the first age of civilization that's not defined by a material, right? We are now in the information age. So that gives us a way of thinking about materials by design, from atoms to structures by design. OK, so information gives us different ways of thinking. That's where the power to unlock the future comes. All right. the challenge in material science is one of increasing constraints. Right, so we're not just saying, I want a new material to make a rocket. We typically say, I want a material that is earth abundant, that is sustainable, that is non-toxic, that is recyclable, that is biodegradable, processable. What you'll notice is none of those words define the properties of the material that you want, and we often start with this now, and that's a complete 180 degrees from where we used to be in thinking about materials. So we haven't said strong, hard, conductive. Those are the properties we're trying to embed in a material. Now, one of the really important things about materials, if you're a non-material scientist, is that all of these properties are not just defined by the composition of the material, right? The properties are determined by how those atoms are arranged. So you've got an added complexity to determination, right? How the atoms are arranged. And materials change over time quite dramatically. So if you are designing or thinking about a material in its pristine or day one use, that might actually be completely the wrong material for 2, 3, 4 years later. It might even be the wrong material for 2 hours later after you put it into use. So these are the things that make it quite complex to think about designing new materials. And in some ways, as an experimentalist, you are looking for needles in haystacks when you're thinking about trying to find a new material. This map shows you the known universe of materials, right from elements to known compounds, organic compounds, whole known species. This number here, 10 to the 7, just proteins in the human body. So what we already know of materials and molecules is vast. But I already told you that the properties, the structure, changes the materials. When you add in processing and structure, you end up with a parameter space that's effectively infinite, right? So what do you do with an infinite parameter space? You have to have some way of navigating that space. And actually, one of the big promises of AI is that it's going to give us a way of thinking about navigation. How do you find, in this vast landscape, the little island of this element, this compound, that's going to have these properties that I want to develop, right? That's where we all hope AI is going to help us. All right. I'm going to just take this as a bit of a case study in one particular type of materials, because, again, I could talk about many things. I'm going to talk about batteries. I don't suppose I have to tell you why we have to think about batteries. In large, I also want to think about transport. So, emissions. This was, and again, there's a story here about scenarios. Emissions 1.0. In the Victorian times, there was a crisis of pollution from how we traveled. And there was a great savior to this pollution. Where did it go? It's coming. Slide delay. Doesn't want to tell you. The car. All right. When we launched the motor car, there's all the things that we currently think about. Convenience, speed, personal access. But one of the great revolutions of the car was that it was going to solve the urban pollution problem that horses had caused, right? Of course, it didn't quite do that. It gave us a much worse problem, CO2. And if you look at emissions from CO2, you'll see transport is one of the biggest pieces. So our solution to that is the electric car, right? We can have another debate about whether this is the right response to that problem. But anyway, this is the trajectory. So the electric car needs batteries, and we've got this concept that electrification is going to be renewable, reliable, and free. But if you are thinking about lithium-ion batteries, this is the projected trajectory growth of lithium-ion batteries up to 2030, right? So you'll see from 2020 to 2030, this massive exponential growth in demand for lithium. The UK has committed to net zero in an act of parliament. There's going to be a ban on combustion engine vehicles in the next 10 years. This growth is driving that. We don't have enough lithium. And if you look at the critical materials for lithium, just for the batteries, we're going to have 3 times the amount of graphite, lithium, 2 times copper, 4 times nickel, 6 times manganese, 2 times cobalt. We cannot actually deliver this with current materials technologies, all right? So we've set in place a set of policies. We've set in place a technology. We actually don't have the raw materials to deliver it. So there's a few ways around that. You say, actually, we are all now going to compete for these materials. We're all going to be competing for lithium and copper and manganese, and we're already seeing that play out, right? We're seeing what's happening to geopolitics because we're competing for these materials. Or we say, why don't we find different materials that can provide some of this function? The other thing I think that is a challenge when you think about batteries and new batteries, and this is a quote from my colleague, Greg Offer, who has got a startup, an AI startup in battery space, that in the battery market there is risk. There is risk everywhere, and all of those risks compound each other. And largely they're these different materials sitting on top of each other in the challenge. Okay. I'm assuming you know how a battery works, but just very briefly, you've got all these different pieces of a battery, different materials of the battery, right? All of them will probably need replacing or increased. You've got current collectors, aluminium and copper. Copper is the element that is going to stop us transitioning, right? Because electrification of everything relies on copper. We don't have any other conductors. The cathode material here is the one where we are really worried about rare earth. Typically, that's nickel, manganese, cobalt material. Again, materials that we don't have enough of, and actually causes some other problems, not just the fact that they're rare. They're also quite difficult. So in case you've never seen it, that's the lithium-ion battery charging. Lithium going into the graphite and coming back out again. If I leave this going long enough, you'll see around the edge of that graphite that's just been lithiated, little nodules that come up. Those are dendrites. Lithium does that. It will electroplate in your battery. What it does when it electroplates in your battery is this. So there's a huge safety issue with the lithium-ion batteries, and we'd like to make it better. The more we try to advance this current technology, the faster we try to charge, the worse all of these problems get. So a lithium-ion battery is brilliant on day 1. On day 2, it's a little bit worse. On day 3, it's a little bit worse. If you drive it, you might get something catastrophic. So it's not been optimized for lifetime. It's been optimized typically for capacity on day 1. So some of these complex challenges we need to think about. Okay, so you can summarize some of the challenges that you are going to need to bring into any kind of AI-based approach if you want to design a new material. And I would just ask you, when everyone stands in front of you and tells you that they are using AI to deliver a new material, have they answered all of these questions? All right? This should be a bit of a test for, is AI delivering what we need it to do? And in the battery space, first of all, we talked about this. The design space is immense, right? So how are we making sure we capture all of that? The interfaces, so you're not just taking a material and using it in isolation, you're putting it together against lots of other different materials. They're complex, and we don't yet know the physics of all of those interactions, right? So we don't understand that. The data are actually quite sparse and inconsistent, right? So we don't have a lot of data that helps us think about this. In real-world systems and in simulations, there's a discrepancy, an incoherence. Have you thought about manufacturability before you start your project? You can potentially find the best material in the world, but if you can't make it, it's not a very helpful process. And then the last thing I just wanted to talk about, often when we think about materials discovery, we're thinking about atomic structures. But again, in this system, we have to think about multi-scale physics and how those multi-scale phenomena are coming together to develop the system or the integration of those materials that will be helpful. So if you can't answer these questions and how you're addressing these questions in what you're trying to deliver, then I would be skeptical. Okay, but these challenges are massive, and AI does give us a really big opportunity in addressing some of those. So I've tried to capture, where is AI going to make a difference now? In some cases, already making a difference, right? Sometimes already seeing this. And where do we need to think a little bit harder about how we do this? So the first promise of AI, unlocking that vast materials design space. And we know there are tools that already exist that can help us do this, and is starting to do this. Predicting properties from structures or for simulated structures without having to do, I made a material and I tested it. I made a material, I nailed a material, I did the X-ray diffraction and I tested it. No, we can do that prediction, and that prediction is quite robust already. We can then even propose new crystal structures, and based on what we know about crystallography, start to understand predictive properties. From that, you can develop, and are developing, and I think you'll hear some more talks this afternoon, thinking about ways of inverse design frameworks that are going to help us target functions and give proposed crystal structures to do that. Materials by design at this level is getting quite a lot of traction. And you can start to embed some of those constraints beyond function. So we're seeing that come through in some of the startups already. What that means is, what it doesn't mean is that AI is suddenly giving us the material, that's the one, go. What it's saying is, don't look at these million materials, look at these 100, right? And so suddenly, the way to think about design and testing becomes a tractable problem. You can also, as you start to do this, of course, access more data. We're going to talk about data a little bit, but every time we do this, we're getting better at what we're trying to do, we're learning. So there are already some really interesting proposed new structures. This material here was designed or predicted by an AI group working in the States. So can we change some of that nickel and cobalt, the really challenging materials, to make a material that has got similar properties, but will be more earth abundant, right? And probably, it's not been tested yet, but probably more stable. So we're seeing some of this already unlocked. Okay. The other thing that AI is really driving, and I think is going to be both a benefit and an accelerator, is integration of computation and experiment. All right, so thinking about the way we do automation in labs using robotic synthesis, thinking about data fusion, how do we take disparate measurements of materials and systems and bring them together? So not just that we've looking at them complementarily, but actually we're getting more insights from those data than we did if we looked at them conventionally differently. So closed loop, autonomous learning ecosystem for materials development. And we are already seeing a lot of labs being set up to try to do this coherently. And that means you can go from 1 million candidates to 100 candidates in hours, not minutes. We've got one of these systems set up at Imperial called Digibat, high throughput robotic platform. So so Ifan and I are experimentalists on this, but you'll see this is a team that brings together a fundamental materials theory and simulation, high throughput processing, and AI. So building a team that does both of those things is really important, right? Having together in a group of thought the way that you think about doing things differently. I'll skip over this. It's a lab that brings together all of these different pieces. We can do like making a material. And a battery is a little bit like a sandwich. You have to put all the bits together. Students spend a long time putting bits together. That introduces a huge number of errors. And just getting a machine to make your sample already cleans up your data enormously, right? So this is an example of a lab researcher. This is the capacity. So how good is your battery? If a researcher does it, you get massive discrepancy. So one day you'll get this, and the next day you'll get that. The machine is the best and reproducible. What does that mean? It means when you start to look at your data, you take out all the reproducibility errors. So your data suddenly now becomes more robust and better useful for your algorithms. You also see this massive spread in performance over time. So when you do this process manually, you introduce a huge number of defects into your system that the automation doesn't do. And we've put here together a digital twin of the lab and this place. So that allows us to do this accelerated experiment design. What is happening with data quality, sparsity, integration? Well, we're already using natural language models to mine literature and patents, right? So how do you pull the data into your learning system, right? You can't, well, you can synthesize some data, but I'll tell you in a minute reasons why you can't do that. And that active learning allows you to say, here are the gaps, let's go and create that data. We're looking at multiple fidelity models and data fusion techniques. But most data sets that you can find don't track lifetime. So if you're looking at those safety pieces, the security pieces over time, those data sets don't exist over a long time frame, and they're hard to get. The other thing that is often not understood is how path-dependent the behavior of battery materials are. So if you were trying to control for two different experiments where one is done at a slightly different temperature and not reported, then the fidelity of your data makes that invaluable, right? So it's very hard without the full physics in your system to really get to a point where you can track the lifetime behavior, right? So we are already seeing we can use real data, we can do it better, we can get simulated data for pristine materials, right? We need to do a lot better on thinking about how we're thinking about these different pathways for design. So this is an example of data fusion, where we are actually accelerating how we think about data by taking a single high-resolution image in 2 dimensions and coupling that with a massive volume of low-resolution data. Using AI to combine these two data systems, you can end up with a 3D super-resolution volume. So typically, it would take us about a week to get these data. It takes us about 10 minutes to get this data, 10 minutes to get this data. So the AI is actually dropping by orders of magnitude how long it takes us to acquire a level of data that is then usable for our models. So you're getting this really interesting feedback loop between using AI to improve data to improve AI for different tools. Okay, this is the really hard bit. Degradation of batteries and safety of batteries. We're starting to use machine learning models to predict long-term kinetics of possible pathways. We're also, actually, and this is where AI is having a big impact in this space, is using it for monitoring, right? Can we be measuring things in real battery systems to look for correlations and weak signals that help us both think about then automatically controlling the system, the charging rate or the voltage potential, but then also feeding that back into our understanding of what's happening. So using AI to develop these really interesting new monitoring spaces. But there's a really interesting and important problem here. This is an emergent, non-linear phenomenon, right? It's extraordinarily path-dependent. And so what that means is that the rules are changing during the process. All right, and if you haven't got the physics in your model, you don't track that pathway properly. So basically, your models have to know some thermodynamics, right? So putting physics into the model is going to be really important. And I think what we are seeing is a lot of the models, some of them are actually getting quite good with just the data, and they can predict things up to a number of cycles. But much longer than that, the lifetime that we care about is still really hard to predict, and there's a massive bifurcation of behaviors. Okay. All right. I want to talk a little bit about what we're doing. Actually, I thought there was a slide that kind of summarized those bits, but anyway, I'm not going to test you on what all those criteria were, but those are the bits, the questions that we need to ask ourselves about materials design. We know where we're already making a difference. We know where we need to do better. And I'd say where we need to do better is 2 things. Much better data. We don't have it, right? So the data input needs to be much better. Much better understanding of the lifetime and the physics of those interfaces, and putting physics into the model, right? So that, I think, is going to be really important. Right now, some of that feels intractable. I think in a few years' time, somebody will be standing here with a quantum AI system that will say, you know that complex problem that Ryan talked about a few years ago? This now works, right? So I think the pace of how we're thinking about AI, bringing physics into AI, is going to be make a big difference there. I want to talk a little bit about what we're doing at Imperial to help some of this acceleration take place. This is our White City campus. It's designed for innovation, so we have all of our innovation assets in one place. In particular, we specifically bring together research, innovation, and corporate partners together in the same space on the same campus. There are 100 different organizations in our campus. Looking at all of our system assets are in the same place. So we have Hackspace, we have an incubator, we have venture capitalists, we have accelerator programs. And we're bringing extensive support for companies that want to do this. So we've created in this space an ecosystem that is probably the fastest ecosystem growing in Europe, and has actually been a bit of a magnet for other places, people to join us. I guess this number, 400 million on our, no, 600 million raised on our campus, that represents on our campus 2% of all venture capital investment in the UK. All right. So basically, we're crowding in not just Imperial startups, but other startups coming to be part of this growth. I'll skip that. One program we've been running in particular is a program called the Super Connector around AI, and it's a way of thinking about bringing together a cluster of companies in a programmatic manner, in a equity-free way. So we bring companies in for a very specific boot camp around AI. We have sponsorship in partnership with Google Cloud and NVIDIA, so they provide all the compute, they provide experts. 6 months free, so it's an equity-free position. And it does a few things. So we're trying to support specifically de-risking of those technologies, and we do that by bringing together technical experts and investor experts to really challenge the startups when they come in. What do you need? How do you think about not just technical delivery, but what are going to be your value inflections when you make certain demonstrations? So it helps from the de-risking space. It gives early access to new technologies, to different investments and corporates. We bring partners together in this program, and we provide, I think this is really important, a really comprehensive assessment of their technology, of their business plan, of their translation pathway, to enable them really to be investor ready. The core principles of our Super Connector programs, it's thematic, there's learning methodology, and it's a sharing process, right? So it really is a cohort of students that we've brought together. We brought 24 students, 24 different AI ventures in the last year. Of those 24 ventures, more than half of them during a 6-month program generated new IP, so it's generating quite a lot of new space. By the end of it, more than half of them had to hire staff to expand their team. Oh God, I should have the number on here. Created investment and investment partnerships. The last one from the last round, Nexus, just closed a £2 million, a very early stage seed round. So it's a program that is focused. It's focused on a technology space, and it's delivering in a short period of time quite a dramatic change. And some of that is really around the principles of the way we've set it up. The other thing that we're doing in Imperial, we've got a large corporate partner ecosystem, and we're very keen that that corporate partner ecosystem also has access to our startup ecosystem. So they shouldn't be set in two different places in silos, right? They need to come together. One of the models that we've been looking at is also how we bring corporate partners to help us with co-founding of startup companies. So from the corporate perspective, they funded some of this early research, but the de-risking sits outside of the core business, which is important. And that does two things. It means that the technology that they want to bring into the core business can be brought in, but it also gives the startup opportunity to look at cross sectors. So this is Solve, co-founded with BASF, and it's an AI rapid throughput processing company for sustainable molecules. The other thing I think that's really interesting is, as a model, the fact that BASF are already engaged gives a confidence level to other investors, right? Because they know there's a market coming. So I guess this is just a map of our different spin-outs, but you can see in the AI space several startups that have been acquired in recent years that are really moving things forward. I wanted to just talk about a couple of startups that have come through our system that are materials related. Polaron is a battery processing company, and it helps think about how you design ways to control the morphology of different systems, right? So how do you optimize for porosity? How do you optimize for particle size? How do you optimize for processing to get to that place? It's been part of a major government recognition. It won the Manchester Prize in the UK is the government prize for AI startups. Last year, it's got seed investment now. It's run our Catalyst Challenge, and it's already working with battery manufacturing companies. So this is an interesting space because it's a materials company, but it's not focused on composition. It's focused on structure and processing and manufacturability of the systems, right? And it's dramatically improving materials behaviors. Monolith AI. Again, this is a company that is looking at how you make data-driven decisions as a way of processing and developing new structures and components. Safe intelligence, looking at how we monitor things. Right? I talked a little bit about using AI to monitor systems, but how do you do that in a way that gives confidence to the manufacturers and where those components are going to be in? And so we're looking at not just mobility and transport, but including alternate pathways. Okay, Solve I just mentioned. So I'm going to stop in a minute and give you a couple of times for questions. I hope I've given you an insight into what it feels like to be an experimentalist when AI is overtaking your world, right? And it's two ways. One, it's really exciting because we are having the opportunity to think about new ways of working, new types of materials that are going to come through, and really a disruption in how we can accelerate materials process. But also, I guess, a caution that we need to do this in a way that's cognizant of some of the constraints of real-world deployment of materials, right? And not just day 1, day 2, but day 300. But AI for materials, this is a report from Status Insights. I like this. They analyzed 450 startups in the materials space, the digital materials space, and the 5 biggest hubs, you'll see London and Singapore, are highlighted specifically as hotspots for where materials and AI are coming together to be very disruptive. It's also a big growth area, so the numbers aren't so huge just yet, but we're expecting this to reach about $500 million in the next 5 years, and it's a growing sector compared to some of the other areas where AI is being deployed for technology. It's already happening for materials, and I think this intersection of where translation and partnership at pace is going to make an even bigger difference. So with that, I think the future is bright, and I'm looking forward to hearing more about what's happening with the AI startups we're going to hear from next. So thank you for your time. Let me stop that. Shape the future. Thank you.
Thank you very much, Prof. Mary Ryan, for the wonderful presentation. Shall we just have a little look whether we've got any Q&A coming in before we officially say thank you?
I have one question. Do you want me to answer it?
Yes, that'd be great.
Okay, one question here. From Abdul. How do you see the role of experimentalists evolve with the emergence of automated materials R&D? What should be the role of experimentalists in the future? Certainly not a mere verifier of AI. So it's really interesting, and it's a big challenge, right, when you think about experimental programs. I mean, I showed you just simply the reproducibility that you get when you have everything automated. We are setting up an entire digital twin for our experimental platform. And I think there's a few things where experimentalists need to be there. There needs to be how are we designing those platforms? How are we thinking about the ways and the process and the methodology, right? So somebody has to think about how we think about designing the methodology. But also, I think there's a really important place for that understanding of analytics of experimental data as it comes through, right? In a way that is looking at the way that physics and chemistry and electrochemistry is coming through the data response. But it is definitely, in 10 years' time, going to be a very different role. And I think the way that we need to pivot now is also the way we're thinking about training experimental scientists in universities. What are we giving in terms of that support package so that we have the right kind of experimentalists going forwards? Okay. That's it.
Prof. Mary, we got one more question coming your way.
Okay.
You have time to take one more?
Yeah, oh, it's coming, it's coming, it's coming.
Thank you.
Okay. This is from Ian. What are your thoughts about the perennial challenges on AI limitations in predicting extrapolated outcomes, and if it will be limiting the bounds of materials discovery? Is physics-informed AI useful? So, yes, 100%. I think the inability currently to predict long-term outcomes by AI is limiting, but it's also limited because we can't predict the long-term outcomes because we don't yet have the full physics understanding of these systems. So, was this you? I think this is where we need to do much more physics in the AI, right? Physics-informed AI. I think quantum AI is going to help us a little bit more with the complexity. But I think we will get to some place where we will get better at it, right? Because we're going to learn the outcomes. We need to do better measurement of long-term data. I think data in and of itself is not going to do us enough. We've got to have, when you've got emergent, path-dependent, complex phenomena, you also have to put physics in as well as data. Right? So yeah, absolutely.
Sarah has one last question for you. Is it okay, Paul?
Yeah. Well, it says I've got time on the clock here, so if you're okay, I should have looked at it first. What do we need more to progress? Seems like everyone is doing the same predictive materials using AI, but I have not seen the real impacts yet. What's lacking? All right, I could talk about this question for about an hour. I think, first of all, I think we need better definition of problem statements, right? I think we just assume if we make a material that is going to have a higher capacity or have a slightly different composition or is going to fast charge, then it will automatically displace the incumbent, right? It won't, right? So there's a huge conservatism in using new materials, right? Because the prediction of materials behavior over time is very difficult. So there's an outsized risk to deploying materials until you've tested them in the field and understood that long time piece. So that is a barrier. So I think confidence, and it's to the question before, it's confidence in long-term prediction is going to be really important because otherwise the risk is outsized. I think also the thinking about not just what the material will do in advance, but thinking about how it's going to fit into supply chains, how it's going to fit into manufacturing processes. So if you have to stand up an entirely new processing plant to make your new material for a marginal gain, that's not worth the investment, right? You have to think about what is currently operating, and are we just going to displace something and get better outcomes, or is it a small investment, or are the gains so disruptive that it's worth that investment? And I think right now, because we can't measure all of these different complex pieces, you can't make a business case for the very disruptive side, right? So therefore you get stuck in a bit of a catch-22. And I think we are going to start to see, I think what we will start to see first are probably more incremental gains. We're going to see incremental gains in efficiency of processing, right? How we make things better that's going to drop down energy costs. We're going to see probably some substitution from earth to more earth-abundant materials because the critical minerals is driving us there. And I think in that space, there's going to be a really interesting question between abundance and performance. Do we still really need that? You know, history has driven materials that perform better. Do we want, is that the trajectory, or is the trajectory I want a material that's going to perform good enough, but be earth abundant and recyclable, right? That's never been the trajectory of technology adoption, right? So we might need a rethink of how we are changing the materials process. We good?
Yes, ladies and gentlemen, can we have a big round of applause for Professor Mary Ryan?
Thank you.
Thank you. If I ever go back to school, I want to take all of your classes. Thank you. Ladies and gentlemen, what a treat it has been to listen to Professor Mary Ryan. And of course, if you'd like to catch her in person, she's going to be here for just a few short minutes. And well done. Here we are, almost at the end of day 2. Now, before I bring on our next speaker, I'd like to remind you that tomorrow is our Community Day. Can I please welcome you back? I know it's a Friday, but if you don't mind, we would love for you to come and join us on day 3 of Switch as well. So tomorrow, the Beyond Stage stage right here will be open for a feature on the AI community, and we will kickstart the day with a session that's titled Scaling AI Innovations Globally. So if that's interest of you, we will see you here tomorrow morning. But right now, bringing us home today